Friedman, and this is Will Byrd, and we are two of the three people who developed miniKanren. The third one is Oleg Kiselyov. We have brought with us 25 copies of a draft of the second edition, and I will
Second edition of what?
Second edition of the Reason Schemer. It doesn't have the elephants. It doesn't have the pretty cover or anything. It's just a draft. But I see that there may be more than 25 people here. So I'm going to figure out a technology where I can get your name and address, and I will send you one. Just for legal reasons, I'm not allowed to give you a PDF. I'm sorry, but that's the way it works. The idea today is to first show you a little bit about our philosophy on how you can just be a sort of garden variety functional programmer and turn yourself into a red-hot logic programmer. A relational programmer is what we like to say.
Red-faced, maybe.
Maybe red-faced, yes. It turns out to be really easy. And so that's the first thing we're going to do.
It doesn't turn out to be easy.
Well,
it turns out to be really, really hard.
You guys know who Dick and Tom Smothers are? Okay, so and then we're going to show you some kind of neat examples that you probably wouldn't think of writing yourself, we hope. And then we'll finish it up with some interesting new work that we're doing on constraint logic programming. And we'll show you some of the famous problems that are solved with those tools. How we'll do this in 40 minutes, I don't know. But we're going to make a stab at it.
By the end of the talk, David will have added everything to core logic.
Of course, yes. And that's the reason we're here, basically, because we found out about core logic and thought, well, we ought to meet the people. And I'm really excited to be here. Will, do you want to say something?
I'm excited, too.
Yes, okay. Thank you.
Oleg, I'm sure, would be excited if you were here. We'll have to get Oleg to come out and visit next
we'll
year.
figure something. So we're going to look at probably the easiest program you've ever seen. It's called append. So is that up there yet? Oh, wait, we have to teach you the language first, probably.
Well, they already solved the language a little bit, but
okay.
Let's
There's
do
the
a
language.
refresher.
You had a really great refresher this afternoon by Ambrose, so we're going to assume that some of that sunk in, and so now we're going to go to the append. Okay. And when we get new stuff, we'll talk about it a little bit.
Fine.
So here is the standard definition of append in virtually every single Lisp scheme, whatever, closure. This is probably how you write it. The only difference is that you probably write it with L1 and L2. And we're writing it with S. Okay, that's just a small difference. But what we're going to do is translate this program directly into miniKanren without any effort. So when you go from a function to a relation, you add one more argument, which is the answer.
Oh, that's not the first thing you do. You have to
You
change
have the name, yes. Appendo. Everything has an O at the end, right? If it's just our little game.
Like Spanish.
If you corner me, I'll tell you why it's an O. But here we go. So it's a function that will take one extra argument, and that's the only thing you have to remember. A function takes n arguments. A relation will take n plus 1 arguments. And the first thing we do is we'll change the con to con-d.
Now, our con-d is not your con-d.
Yeah, our con-d is completely interleaved. It uses what I like to refer to as a distributed trampoline. And I can't explain that in the time we have. But the code is all there in the back of the book on one page, one little page. All you have to do is spend about a year looking at that page of code, and you'll be all set. Okay, so con-d is the same, sort of like the con-d that Ambrose talked about earlier. And the first thing we want to do is we want to mimic the behavior of the append. So it says, is the list empty? So the way we ask that is we ask, does it unify with the empty list? And that's all we ask. And now, if it does, then that's an answer. We're happy with that. So we allow out. Oh, you called it ls. I call it out.
I know, that's not
Change it to
classy.
out.
No,
I'll forget
that's
which one
an
is
evil
which.
bad habit.
Okay.
Okay, fine.
Thank
I'll
you.
change it to out, but you have to forget that I ever did this. You shouldn't be thinking of in and out variables. That's
You shouldn't,
for
but that's not the metaphor.
Yeah.
Okay, so out will get unified with the result, which is just the empty list again.
the empty list.
L.
Are you defining the same append I am?
Oh, no, S, yes.
Do you know how to define append?
No, it's the S over here. So it's the S. Okay, so now we...
As a book I can recommend.
There is a book. It's all in there very clearly. Okay, so the next line, which is the last line, so we're mimicking this, is to say, all right, we want to run this piece of code, okay? But we can't because we have nestings, and we don't know how to deal with nestings. So we have that cons, which is wrapping the append. That's another use of the word wrap, maybe. And then we've got things like cdr and car, which are not really they're functions, they're not relations. We want to turn them all into conventional things. So we'll start very easily by saying, let's just do the car first. In order to do that, we're going to have some sort of out variable for it, because car takes one argument, and we're going to use, do you want to use car?
No.
No, okay.
I'm going to show you the right way to do it.
Okay. So we're going to...
I mean, you've got Caro. Caro is cool, and Caro's in the book, but
Okay.
this is the way, like, the pros.
The pros. So we're going to introduce fresh here, which introduces some variables. And we're going to call the variable A because it's for car. Okay. And you can guess that we're probably going to want a D too, so we can throw that in now if you want. And now what we want to do is simply say, well, what is this going to be? What is L going to be? What's going to be a list with A and D? And I'm sorry, you'll excuse the term dotted pair, but that's the way we think about this. So A dot D, which is car and cdr, will be associated with L.
Does closure have the back quote and comma type thing? I don't know what this is. The equivalent in closure would be, but tilde. Okay.
Yeah. So now we have taken it apart, and so that's the car and the cdr. We've already pulled those pieces out. Now we want to take the recursive call of append and use that D as the first argument, S as the second argument. Oh, this is a recursive call. Well, we're going to need another variable because that's the result of calling the recursion. So it'll be, we call it res for result. Now we're almost finished. Now we have to just do the cons part of this. We're going to cons the car onto something, but the car is A, so we're going to do back quote A dot res onto out. Okay? So that's all it takes to write this code. Now, there's a law called Will Byrd law that says...
Oh, no, we're not going to get that law
We're
yet.
not going to get to that law yet.
No, we're going to show them the hard way.
Okay. Mm-hmm. Oh, cons. That's all.
Yeah. My prologue was like a vertical bar or something.
Yeah, it's a... No, it has nothing to do with that. Absolutely not. You can, it's the only way, well, it's one of the, cons is an operator that allows you to create those, but it has nothing, these are all lists as far as we're concerned right this moment. Okay, so we can, yeah, thank you very much. All right, I need to stop doing that and looking here. All right, so we'd like to test this now. So let's try it. Run star, Q, appendo, A, B, C, D, E, F, D, E, and Q. All right, see if it works. And sure enough, it returns one answer. Remember, you don't have to look at those other parentheses if you don't want to. It's only when you have more than one answer. So that was pretty nice. Could we maybe, that would be nice. Let's see what that does anything. So what do you suppose that's going to return? Well, obviously it has to be the list DE, and sure enough it is. And then we can just do one more. And
Oh, oops.
Put the DE back in there.
I'm full of nub.
DE,
Okay.
yes. And now we'll see if it returns us ABC, and of course it will. Oh,
Not.
gosh. What happened? Well, now we can bring up the Wilbur law, I believe. Is that right?
Yeah, I think
Okay. So the Wilbur law says never put...
Well, actually, let's do a run one.
Run one, okay.
Ooh,
Ah, well, there you are.
let's do a run two.
There you go.
So we got one answer. Let's go for double jeopardy. And
Now, you see, we'd like for this to terminate, but it won't. So we violated the Wilbur law. The Wilbur law says you have to always put your recursions last. And now we can try it.
yeah, so basically, whoops. We had something like that, and now we want that.
And here we go. And run it.
And,
Run more.
and the regression tests, like, should run forward. Okay, so now
Okay.
it runs in all the directions.
Okay, so that was easy, but we want to do some fun stuff.
Oh,
so.
whoa, you're not going to talk about why it...
No? You go
Okay.
ahead. Go ahead.
All right. So, what happened with the old bad program was when you have these two clauses swapped. Well, I'm not going to do the trace of it really, but the problem is when you do a run star, you're saying, I want all the answers back. Or if you do a run two, I want at least 2 answers back before you show me anything. And in this case, there's only one answer. So, as Ambrose showed, you have the search tree, and there's all this backtracking and all this nastiness involved, which you shouldn't really think about when you're writing these programs. But that stuff is going on, and the problem is the system isn't smart enough to know that there isn't a second answer. So if you do a run one, you're fine. If you do a run two, well, the system hopefully would fail, but in this case, because we have the recursion before the unification that could make it fail, it's just going to search forever. Okay, and this is a very important principle of logic programming that failure and divergence are indistinguishable. That's a very deep sort of theoretical result. There's nothing we can do about it. But as a general rule, you want to make your recursive goals come at the end of any sort of conjunct. And then the fun part comes when you have multiple recursive goals, right, because they can't all come last. And that's when you call Olig.
Yeah. Okay. I do. But, anyway, so let's try something a little more juicy. Let's try x. Let's introduce 2 variables, x and y. Run star q, x, fresh x, y. And now what we're going to do is a little strange, but we're going to do it anyway. Equal q to backquote xy, comma x, comma y. So it's going, no, yeah, that's right. So the next line we're going to put in, however, is a call to appendo. And this time we're going to say x, y, and A, B, C, D, E. And we'll run that.
Did I, I think I'm full of nub. I changed the...
Oh, you went back. Thank you so much.
Oh, whoops. Hold on. When you do logic programming, you get used to, you embrace the infinite loop. Okay, here we go.
And there they are. Okay, so that's what you'd kind of expect. But, of course, things can get much more complicated than that, so let's make them more complicated.
Okay.
Let's put in a dot, comma, z at the end here. Okay, I think that'll make it pretty complicated, but let's get rid of the star, because I think that would be a big mistake. So let's just make that, like, say, run 5. And there they are. You remember seeing the underscore dot 0. Those answers are perfectly correct, and they're fine. Okay, so what we've so far shown you is that you can take conventional functional programs. I'll just say, I don't like to advertise, but just typical the first 7 chapters, a little schemer, would be functions that would fall into this pretty easy approach. And of course, once you've done that a little bit, you start getting comfortable, and you start working out of the balloon that you started out in. Now we're going to show you some pretty interesting stuff. Ready to do the interpreter?
Oh, okay, sure.
Okay.
Let's jump to that.
So let's write an interpreter.
Oh, we're going to write it?
Well, show it to them.
Okay, well, sure. I mean, I wrote it
It's
while
already written. But,
I wrote it while listening to the last talks, but well, I saw that Ambrose showed off the type inferencer, right? So we're like, okay,
there goes
got to
one
show
of-
something. Yeah, we
there
were going
goes
to show a
one of
type
our-
inferencer, so it's like, well, now
But we were going to run
it's
for
like, we both showed up to the ball with the same
same
dress.
dress on. Yes, go ahead.
Okay. Yeah. All right. Which? Oh, here it is. Okay.
So you can see the language by just looking at the parse. Let's go through the
okay.
parse real quick. So the language has numbers, it has variables, it has the primitive 0 question mark, it has subtracting 1 primitive, times primitive, if, oh, this is the match. Oh, look at this.
Yeah.
This is kind of neat, okay? For those of you who haven't seen something like this is called a catamorphism. If you look at the ifs, the if line, those are recursive calls in the pattern match. So that when you go to the right-hand side, there's no recursions.
Yeah,
That's a kind of
T gets bound to the value of calling
it's
parse
kind of-
on T.
But
And
this
then,
has nothing to do with miniKanren.
Yeah.
This is just a little simple parsing trick.
but you should have that. It's like awesome.
So
It's
we
great
have
for writing.
if and else, we have let, we have lambda, and we have applications.
Yeah.
And, gee, you have to use APP?
What?
I'm surprised.
Well, it has to be tagged.
Well, it has to eventually be tagged,
Oh,
but not on the way
Oh.
in.
good point. All right, I probably just broke it.
Probably. Okay, anyway, so that's the little language we're going to program in. And we're going to write we're going to look at an interpreter. I have to tell you that if we were using match-E, this would be a lot shorter, but we're not using it, so it's a little longer. But basically, we're using just the simple tools of run or run star, equal or unify, fresh, and cond. That's all we're using. Okay, so if we were to be using match-E, it's just a simple little macro that gets the job done. All right, so you can see everything. It should be all pretty obvious here. We're still using the out variable to indicate where the answer is going. But of course, that's just noise, really, because the names don't matter anyway. So we have a lot of fresh variables we're introducing, and that's just to do pattern matching on the kinds of expressions for the most part.
Yeah, they should be locally scoped, but I was lazy.
Yeah, we could do that, but it wouldn't fit on the screen. Well, this much wouldn't anyway. So we have this little language, and now we're going to run it and see if it does, in fact, do an interpreter, does the work of an interpreter.
Oh, yeah, we also have numbers in our system.
Oh,
and,
yes.
And not the numbers Ambrose showed, not the piano numbers, but these are what I like to call Oleg numbers. These are binary list representations. So you'll see those.
Using Indian.
Little Indian
style.
representation.
Okay, so here we go.
All right.
And they are all numbers, as far as I'm concerned. And we've loaded it, and now we can test it.
All right, so
I
let's
presume
do,
that you have some tests that have APP sitting around in them.
How about, oh, I know what to do. Let's do, well, this one's cool. This
You
is a
have
cool
to get
test.
rid of your APPs. Oh, you don't have any in there. Okay.
Shouldn't.
All right, so here we go.
All right, so there's like no point running this forward because that's boring. Let's just run it backwards. So here we're going to generate 30 programs that evaluate to 6. Let's see what it does. Here we go. Sorry, I didn't have time to write an unparser. Okay, so the first one, okay, so we've got this little Indian binary notation. So the first number is 6. That's just like 1, 1, 0. Second one, we're multiplying 1 by 6. And then we're subtracting 1 from 7, and we're multiplying 6 by 1. Here we have a let, and we don't even use the variables. So we're saying, hey, we got some variable bound to a number, and then the body is 6. That's classy. If 0, this is 0, is 0, then 6, else we don't care. Multiply 2 by 3, so we just factored. Yeah, let's find what's the app. Oh, or here's some.
There shouldn't be any apps.
No, why not? There should be apps.
Because Let picked it up.
Oh, yeah, is there
Do you
Lambda
wanna
down
go-
there?
Do you want to?
There should be apps. No,
there won't be.
there were apps. Why would Lambda?
Well, we'll see. We'll see. Run it for 40. Run it for 50.
All right. There should be. I did. Yeah.
There we
Here's
go.
some
There's an
apps.
app. All right. There you go.
Okay.
Can't beat that.
This has to be a really awesome app, I'm sure. Let's see. We're applying some function with an argument we ignore, whose body is sub 1 from 7, to a number whose value we don't care about.
Right.
Welcome to our world. So an interesting research problem is to make it try to generate interesting programs. In particular, the answer, if you take Dan's class, the answer to everything is 120 because he's really big on factorial 5. So our dream is to put in 120 and generate factorial 5 using the poor man's Y Combinator.
We can hope.
That hasn't happened, but
Happened yet.
you can instantiate most of the program and it'll fill in a tiny bit.
Yeah, one of the things about the system is you take a structure, a program that you might want to generate, and you don't have to have all the pieces. Like you could just put in the recursion, for example, that you think you want, or just another call and see if it's smart enough to figure out the recursion. So you basically give it like a template with a bunch of blanks.
Should we try it?
Sure can try it.
Okay, hold on. I didn't practice this part.
Get rid of that app.
What was that?
Get rid of the app.
Oh, yeah. No, only if I parse it. If I don't parse it, it's fine.
Oh, you didn't parse it.
Yeah. Okay. So let's do a run, star, Q.
Q.
Yeah.
It doesn't have to be Q, by the way. It's any lexical variable you would
Okay.
like. But
So,
it shows
wait,
up a
here we-
lot for some reason.
Here we go. Lovely definition of factorial. And I'm just going to run it forward and make sure it's working. Here's the empty environment. And we want to get the answer to that. Let's see if that works.
It did not.
Oh, wait, hold on.
Want to parse something?
Oh, did I?
Why'd you have to parse this?
Oh, I tagged things. Very naughty. Okay, that part of the demo will happen later. Actually, wait, there is one that has facto. I think this test is running, so what did I do? I must have done something wrong. Yeah, that works. Okay, let's just try this again.
That could be an Emacs bug.
No, Emacs doesn't have any bugs. Let's do, here we go. I should be able to feed that in. Okay, see if that works. Okay. All right, now is the fun part. So we know that the answer is, 120.
And we all know how to write that in binary.
Okay, so we're going to feed in the answer. Okay, now we got success. All right, so now what we're going to do is we're going to replace part of our program here. Let's see if I do this without messing everything up. Okay, so let's put in, I don't know, a Q right here. See, that should be var F. So let's do a run one, not a run star. Whoa, what is that? Oh,
That's correct. We never know what this thing is going to return. I'm telling you.
it likes to cheat. It likes to say, hey, you want 120? I'll give you back 120. And yeah, here's just, nested lambda. Okay, so let's Just try to get another answer back. This is always a show. What is it?
Only gave you one.
Yeah, let's do 5.
There you go.
Yeah, that's. Oh, yeah, bar F. There it is. Yeah.
Yes,
High five. Yeah, okay. Okay.
Anyway, so you see the idea is you can take an interpreter, you can run it backwards, and you can run it forwards. And you can take something that looks sort of like the program you want to generate, but fill in some pieces yourself. And it's a game. You have to get to play it yourself. And I don't know where it can take you. I have not the slightest idea at this moment. It's definitely in the realm of research. Maybe research nobody cares about, but research nonetheless.
Research we thought no one cared about until coming here.
Okay, so now let's switch gears completely, and let me introduce to you miniKanren, which is the constraint system that we have. Let's just run some little simple programs.
All right. So you just want to do like a little.
You get a little FD,
Okay.
program. So we added basically, there's something called finite domains, finite domain constraints, and then there's disequality constraints. Now, finite domains are the sort of, how did it come about? Well, because people wanted to solve send more money. So if you haven't heard about send more money, just think to yourself it's a cryptarithmetic problem for doing with addition. So it's send plus more money. And you're supposed to come up with the numbers associated with those variables. So people discovered that if you tried to do that in logic programming, it became very expensive. Someone along the way discovered that you could do it using constraints because no digit is going to be bigger than 9.
Here's send more money.
So you don't have to worry about it.
There you go. So
there's the statement of the send more money.
Cryptarithmetic.
But, by the way, if you go to the Scheme Workshop 2011 page, our paper is there, and you can, you're free to download it, of course. And the answer to these questions are in the paper.
Should mention that Claire Alvis
Yes.
implemented.
Yeah. Well, we will get to that.
Yeah.
Okay, so this system is inspired by the fact that at one time I was reading in Pascal Hendrick's book about how fast their 8 queens chess solver was. And they could do a 63,000 by 63,000 chessboard really fast for solving the 8 queens problem. That's a lot of queens. So I thought, I got to understand this. I have to figure it out. And so Claire Alvis did. And she's graduating with a master's this spring, the end of spring. So let's just do a little simple one. Let's do a run.
Whoa, I already got a couple things.
Oh, you have some. Okay.
Hold on.
Okay.
Okay, so first of all, we've got a couple operators we're adding to miniKanren. So we have a domain operator. You can associate a variable, a logic variable, with a domain. Say, okay, so whatever happens, its value, if it has one, has to be one of the values in this domain. And if not, then we fail. So here we're associating Q with values from domain 1, 3, and 4. And if we run star, we say, hey, okay, well, Q could be 1, 3, or 4, not a surprise. So that's the first part, is domain. And then after that, you can start using constraints on those. And of course, unification, equal, actually is a constraint. That's one of the constraints over trees. So equal works like you might expect it to. But we've added a few other constraints. So we have less than equal over numbers and addition, disequality over numbers, and all different, saying that all the variables in a list, or all those items, have to have different values. So here's a disequality.
It will be easy to add more. It's designed to be really easy to add more.
In fact, For my research, I'm working with Claire and Eric Holk on a compiler for GPU programming, for declarative language for GPU programming, and we're writing a type inferencer, and of course we wrote it in miniKanren. And it turned out that when we wanted to type integers and have integers, have 64-bit integers versus 32-bit integers, that sort of thing, we had the problem of getting multiple types back and wanting to have a preference. I think someone mentioned that earlier today. So we added a preference constraint, and
It's easy.
it was easy. And
It's easy when you
type inference. We removed all the hacks, all the cut type things that we had to use to get it to work temporarily. Okay, so disequality constraint just says that Q cannot be 3. So since Q is in domain 1, 3, 4, then Q has to be either 1 or 4. Pretty simple. And yeah, so the nice thing, in many constraint systems, you actually have to declare the domain of the variable first. In our system, because we believe trying to be as declarative as possible, you can always reorder the goals any way you want. So it doesn't matter. You can declare the domain at the end of the run and it still works correctly. And then you can have a range of numbers. So here we go. Can't be 3, so it has to be 2, 4, or 5. And
That's a good one.
that's a good one? Okay. Yeah, so here we have addition constraint. So we're saying x plus y equals z. Of course, you've already seen the other numeric system we had, the Olig numbers as we call them. But the problem is that those aren't very efficient. And they're also hard to read and all this. So this gives you a chance of...
But to defend the Olig numbers, when you put a variable inside one of those Olig numbers, either after the dot, the end, or somewhere in the middle, you get a whole lot of numbers. One Olig number is worth millions of numbers.
Yeah, that system's actually much more general.
Much more general.
If you're doing something like send more money, you don't need the full generality, and you can say, hey, I know my numbers are between, 0 and 9 or whatever.
This inFD is like dumfD, but it takes any number of variables.
Yeah, so here we're saying x, y, and z are in the range 1 to 5 each, and we're adding x and y to get z, and then we're going to see what the values associated with x, y, and z are. And we get a bunch of sets of values here. So let's see, 1 is 2, and 1 and 2 is 3, and 3 and 1 is 4, blah, blah, blah. Yeah. Et cetera. Okay, and then we've got less than constraints. That's boring. Let's do something fun. Let's do, you want to do send more money?
I think it's time.
Okay.
We'll send some more money.
Okay. So let's grab that. I know what I want to do.
Now, we don't have multiplication constraints, and one of the ways of implementing send more money is to use multiplication constraints. What I wanted to be as simple as possible. I wanted the language to be something that you'd say, well, gee, I can not only understand what it's doing, but I can read the implementation. So anything that we were willing to sort of leave out, we left it out. It's easy to add, yeah, I assure you. It's a walk in the park.
Okay, here we go. So here's send more money. And so the way you can think about it, let's see if I bring up the puzzle again, so you can see crypt arithmetic. So we've got our letters up here in our fresh, SEND, MORY. And we want to get the answer back. We want to know what the values of all those letters are. The first thing we do is we say that all those letters have to have different values. They have to have different numbers associated with them. The numbers S and M, actually most of the numbers can range from 0 to 9, but we know S and M are special because they have to be 1. They can't be 0. That's part of the problem. Part of the problem description that the leading numbers can't be 0. So that range is slightly different. And then in order to do the addition properly, we're going to have some carries, and the carries are going to have either value 0 or 1. And now we just do some long addition. So we're going to add those pairs up. S plus M is going to give us a carry bit and output variables, so forth. And then we can look at the long addition, which is sort of what you would expect it to be. So when you add two numbers and a carry-in bit, then you're going to carry out bit and a digit. And we know that the total sum will be between 0 and 19 because the two numbers coming in are between 0 and 9, and we've got a carry-in bit that could be 1. And a partial sum before we add the carry bit is going to be at most 18. So we just add those up. We add the partial sum with the carry-in bit to get the total sum. And then we have, to give the carry-out bit, we have a choice. So either the sum ends up being greater than 9, in which case we need a carry-out bit, or we don't. The carry-out bit is going to be 0. And in fact, here, when we need to do a carry-out, we have to subtract 10 from the output digit. So here we're using addition for subtraction, which is one of the nice things about having a relational operator. All right, so let's run it.
And there it is.
Dare we time it?
Sure.
Yeah. Pretty fast. Okay, so that's send more money. Mm-hmm. And there's N queens,
we
but
have
do we want to do
yes,
N?
Okay, the queens,
do N.
Sure, we should do
All
that.
right. Okay.
Now you know, probably, that the 8 queens problem has 92 solutions, right? So we're going to show you
Everyone knows that, Dan.
all 92 solutions. And
Okay.
And maybe we'll even time it. I don't know. How much time do you have?
Anyway, the code we give in our paper is nice, and it can work for N queens, but it's not very readable because it's so general. So I kind of unrolled those loops, and here's an 8 queens version of it. Basically, the way you can think of it is a chessboard. We're only going to be looking at the columns of those boards. We want to have a number associated with each column, A through H. And we have this constraint, all different, with that across those values to make sure that basically you don't have 2 queens in the same row. We already know that we don't have 2 queens in the same column because we have them in the list. It's the same length. And each queen's position can range from 1 to 8. That's what we have here. And then the only other thing we have to do is make sure that queens aren't attacking each other along a diagonal. So here you can say, okay, well, if you have a queen in the first column and a queen in the second column, their positions can't differ by exactly 1 because then they'd be along a diagonal, either going upper right or upper lower right. And similarly, and as you go to the right of the board, since we're not worrying about going to the left, we already handle that. In the out, sort of that's the way we describe the problem. You only have to add the constraints when going right. Then the number of constraints you have gets smaller. And then for each of these diagonals, we have to use addition and then this disequality constraint to make sure that you're not attacking along a diagonal. Okay, so let's try that real quick. I might as well time it. Okay, so those are all the answers.
1.7 seconds?
Yeah, that's all right. We have, so right now this is running our Shea scheme, or sorry, this is a petite Shea scheme, so this is an interpreter. Under the compiler, it's a lot faster, but it's relatively fast. It's not going to do 64,000. But the nice thing about it, as far as performance goes, is that if you reorder the goals, your performance is still roughly the same. And that's not true of miniKanren or Prolog or something like that. Normally, if you're just doing regular logic programming, if you're not cutting off that search tree as aggressively as possible, you start swapping goals, and something that used to come back, in milliseconds can take hours or a million years, or in the worst case, diverge. So that's the nice thing about having a constraint system is that the performance is going to be similar no matter how you reorder the goals.
Let me tell you a little bit about some of the things we're thinking about. We have implemented something called alpha-Kanren, which basically allows you to do alpha equivalents of 2 arbitrary lambda terms, or to the universally quantified terms or existentially quantified terms, whenever you have a binding kind of operator. And it turns out when you want to write a type inferencer, for example, that's very useful to have that skill.
I got to show the bug.
Oh, yes. I
forgot. Okay, yeah. There's one really cool thing we got to show you still. Okay.
We have to show you the bug.
Yeah, we got to show you the bug.
There is a bug in Ambrose's borrowed type inferencer.
Don't say it that way. That's so cool.
Borrowed type inferencer. But only because there was no way that you would know that was a bug. So we're going to show you.
We're going to show you the bug and how to fix it. But anyway, So the nominal logic stuff, the alpha Kanren stuff, that is derived from the work of Andrew Pitts and Cheney and Lakin and all that. Okay, so let's... And Urban, that's right. Can't forget Christian Urban. Okay, so let's go back to Arvallo. Okay, so here's our interpreter that runs backwards. And let's end with a bang. Let's show you a little problem with our lookup function, with our environment lookup. Here we go, apply invo. Okay, I'll show you the bad one first. Okay, so here's our apply invo, and this is basically just like an ask you type thing. Ask you and then taking the coder of it. You want to look for the variable in the environment, and if it's there, give you back the value. Otherwise, recur. Fine. So I'm going to come out for a second. Okay, we're all happy. Now I'm going to come out and load the bad definition. Okay, so here we've got a nice little let program, and so let x be 3, and inside of that let y be 4, and the body of that inner let is just y, so y should be 4, which in Oleg representation is 0, 0, 1. So let's see if that works. Okay, it passed. Let's try this next test. Okay, so the only difference between these two programs are the variables. They're actually alpha equivalent. So instead of having an x and a y, now I've got an x and an inner x. Okay, so this should give you the same answer back, right? All right, probably know what's going to happen already, but let's try it. Oh, actually, you might not know what happened because I forgot what happened. Okay, yeah, I thought it was just going to give you the wrong answer, but of course what it does is it gives you the right answer and the wrong answer, because that's how logic programming works.
That's how our implementation.
Yeah, okay, so we got 2 answers back. So we got the answer 4 back, and we got the answer 3 back. So what's going on here? Well, what's happening is we're getting both of the bindings in the environment. So x is bound to both 3 and 4. We're shadowing x in our environment with this representation. And if we look at or apply invo, what's happening is there's no, here we're checking to make sure that the variable we're looking up, x, is actually the first thing in the environment. But in this other case, we're basically saying, hey, just recur. And in logic programming, unlike in functional programming, if you have a cond, or the equivalent of a cond-e, you take both branches. And the branches don't know anything about each other. So just because we took the first branch and found an answer doesn't mean we're not going to recur. Okay, so what we need to do is actually cut off that recursion. Here's the correct version. What we need to do is have a disequality constraint saying that it must be the case in the second clause that the variable we're looking up isn't the first thing in the environment. And that's enough to cut off the search, and then we only get back the correct answer and not doing weird things with scope. So that's an example of a type of constraint. And I think there are disequality constraints in core logic right now. Is that right? Okay, so constraints over trees.
And now it runs?
Oh, yeah. Well, that's the version I had before.
Oh, okay.
But, yeah, let's make sure it still runs. Yeah, now it works.
Okay, so one of the things we did do that was kind of interesting is we took first-order predicate logic and wrote a little theorem prover in it. This was work we did with Joe Neer, who's just about to leave, I'm hoping to leave MIT, and maybe coming to Bloomington, I don't know. And we had to figure out a way to run it backwards, because that's the game we play, right? It's not an interesting program if you can't run it backwards. So sure enough, Joe figured out a way to run it backwards, and it was generating things like modus ponens, which is kind of neat. And if I was all that interested in the topic, I probably would have run it for $1 million or something and see what other theorems it was producing. But we just wanted to demonstrate some of the neat things you can do with logic programming. So we hope you have some better appreciation now about why you might want to get involved in the stuff that David is working on, and Bros. And thank you for letting us entertain you.
Yeah, thank you.